The action potential. Action potentials are the fundamental means of communication in the nervous system. Action potentials represent rapid reversals in voltage across the plasma membrane of axons. The plasma membrane is selectively permeable. These positive feedbacks are mediated by voltage-gated potassium and sodium ion channels found in the plasma membrane. The distribution of voltage-gated channels along the axon enables the conduction of the action potential from the nerve cell body to the axon terminal. At the synapse, the electrical signal is converted to a chemical signal that is then propagated to the postsynaptic neuron. The action potential can be divided into 5 phases: the resting potential, threshold, the rising phase, the falling phase, and the recovery phase. When the neuron is at rest, only a small subset of potassium channels are open, permitting potassium ions to enter and exit the cell based on electrochemical forces. It's important to remember that there is no net movement of potassium ions. For each potassium ion that leaves the cell, another returns, maintaining the membrane potential at a constant value. Before I explain the sodium-potassium pump in greater detail, it is important to remember a few basic things about ions. Positively charged ions have less electrons but a higher electrical potential, while negatively charged ions have a surplus of electrons and a lower electrical potential. In addition, it is important to remember that an excitable cell's resting potential is negative 70 millivolts. Extracellular refers to solutes that are outside of the cell, while intracellular refers to solutes and things that go inside of the cell. Resting potential. The activation gates on both the sodium and potassium channels are closed and the membrane's resting potential is maintained. Threshold. A stimulus opens the activation gates on some sodium channels. Sodium ions influx through those channels, depolarizing the membrane. If the depolarization reaches the threshold, it triggers an action potential. Rising phase. Depolarization opens the activation gates of most sodium channels, while the potassium channels' activation gates remain closed. Sodium ions influx makes the inside of the membrane positive with respect to the outside. Falling phase. The inactivation gates on most sodium channels close, blocking sodium influx. The activation gates on most potassium channels open, permitting potassium influx, which again makes the inside of the cell negative. Hyperpolarization occurs when the membrane actually repolarizes beyond the resting membrane voltage. This undershoot occurs because more potassium channels are open at this point than during the membrane's resting state, allowing more positively charged potassium ions to leave the cell. The recovery phase is the membrane's return to a steady state, as the additional potassium channels that opened during the action potential now close. The membrane potential is now determined by the subset of potassium channels that are normally open during the membrane's resting state. The membrane is now back at negative 70.